So, good morning everyone. Today I'm going to present research work appear in AISTATS this year. So the title actually doesn't ring a bell about recommender system, right? But it's actually can be used to solve a very important problem in recommender system, which is recommendation retrieval. So let's first talk a little bit about recommender system. So some of you may know that when we talk about recommender system, the data we have usually users, items, and user feedbacks, maybe in terms of ratings. And the typical goal of any recommender system is to find a set of limited items which have highest chance to be consumed. And a typical recommender system will have two phases. The first phase is learning phase, or we usually call the training phase. And the second phase is a retrieval phase. And each of these phases has its own concern and issues. For example, for the first phase, we want to have some accurate learning model. And in second phase is we want to have a very fast retrieval system. So usually in the first phase we have the data about user ratings, and then we want to build a model which can predict accurately the user preference. And then the output of the first phase is used to make the recommendation. And during that phase, we need to do the retrieval task. So one of the popular technique for the learning phase is magic factorization. For some of you who, for those of you who haven't known magic factorization, I'm just going to summarize a little bit. So you have a rating matrix of M user and N items. And what you want to do in this learning phase is you want to learn a low dimensional vectors for each user and low dimensional vectors for each items. And the idea is that you try to fit the rating value by the inner product between the user vector and the item vector. So the user preference is now computed through the inner product between the user vector and the item vector. Okay. So now I'll move to the retrieval phase when we actually do the recommendation. So let's say you have a user vector who sends a request, and in order to recommend the items, you need to compute the inner product between that user vector to each of the item vector. So you can get the score of the user vector and item vector for all the item vectors, and then you rank that score to make the recommendation. Okay, so you got the procedure, right? So now we have the problem is that in real life system, the number of items is usually extremely large, meaning that when in ideal case, if you want to compute the inner product between the user vector to all the item vectors, it is very expensive task because you need to compute using brute force approach. You compute the inner product between user vector through all the item vectors. That's the first problem. And you can say that you can do pre-computing, but in real system, it turns out that pre-computing is not practical, because in some system you don't have this user vector until the time of retrieval phase, meaning that you can only get this user vector when you do the retrieval, when you do the recommendation. So pre-computing is not practical in this case. So now an alternative solution which addressed by this paper is to automatically discuss irrelevant items per user. So meaning that if you automatically remove irrelevant items, so that you reduce computational space, right? So just imagine that if you can cut half of the number of items, and you can just do the computation for the other half. So they can save a lot of time for computations. Okay, so that's what the proposed model in this paper does. All right. So how does the model do it? So it exploits the structural properties of sparse vectors, sparse factors, as well as inverted index representation. So let's first talk about the sparse factors. So I have two definitions here. The first definition is conflict sparsity patterns. So let's imagine you have two sparse vectors. The first vector, second vector. So you can see that the non-zero indices of the two vectors are different, right? So we call these two vectors have conflict sparsity patterns. Whereas in the second case, you have the two vectors, two sparse vectors, but they have the same non-zero indices. So we call them, we say that they have similar sparsity patterns. So conflict sparsity patterns are vectors. When you compute the inner product, right? The inner product of these two vectors will be 0. And the inner product between these two vectors will be greater than 0. Okay. So imagine that irrelevant item for one user is when the inner product between the user vector to that item vector is more or less 0. So by removing irrelevant items, it means that you try to remove on the vectors which has conflict sparsity pattern with the user vector. Okay. So about the inverted index representation. So just imagine that you have an index of all the items in the system, in which you will store for the first column you store all the item which has corresponding non-zero value at that index. Okay. So meaning that item 1, item 4, and item 8 has non-zero value at the first coordinate. Similarly with second, third, and so on. So now, if you have a user vector at the retrieval phase, let's say the user vector is 30010. So you can see that the 0 value here doesn't affect the inner product between the user vector to item vector, because 0 multiplied by any value, it will be 0. So this zero value doesn't affect the inner product between user to item. Okay. So meaning that you can just choose to examine the item which has overlap non-zero index with the user vector. In this case, two set of items that are routed in the red rectangle. So imagine that this is a whole set of items, and now you can just reduce the number of items to just 1, 4, 3, and 8. Meaning you can reduce half of the number of items to do the exact computation. Is that clear? Sorry? I'm just showing you an example of sparse factors and example of inverted index representation.
You say the key point here is the 0 to multiplication between 0.
Sorry again?
So the point here is the 0 value, right?
Yeah, the non-zero indexes.
Because map the user vectors
Hmm.
is really hard to understand.
Yeah, I'm not saying that this will be the final. It is. I'm not saying that is the output of the MF models. So this assume right now is we have user and item vectors are all sparse vectors. Okay.
This is that something first we like shown as a MF.
Okay. Okay. So the problem with this approach is that most MF models, the output, they are dense vectors, right? They are not sparse vectors. So the solution is we make dense vectors become sparse, right? So that's what this paper addresses. So let's move on to the problem formulation. So a general formulation is you have n factors which lie in the unit sphere, and the compatibility score between any two factors is computed using this formula, which is an inner product between the two factors. So the goal is to find a mapping function from the unit sphere to higher dimensional space, so that you map one sparse factor to one dense factor to become a sparse vector in higher dimensional space. So this mapping should satisfy two properties. First property is high compatible factors will have similar sparsity patterns, and low compatible factors should have conflict sparsity patterns. So I hope that you still remember the concept of similar sparsity patterns and conflict sparsity patterns appear in the last slide. Okay. So just one small note is that in the context of recommenders system, we can concatenate user vector x and item vector y to receive the factors matrix z, and the compatibility between the user and the item is actually the inner product between user vector and item vector. But you need one assumption, which is the norm of the two vectors are 1, which is not reasonable at this moment. Okay, but just assume that they are norm vectors. Okay. So now, because all the vectors are on the unit sphere, so we need to care about one concept, which is the angular distance between 2 points on the sphere. So xu and y are 2 points on the unit sphere sk, and the angular distance is computed using this 1 minus cosine similarity. So with the assumption that the true vector has norm 1, you now translate this formula to 1 minus the inner product between xu and yi. So with that, the goal is now translated into you try to find the map which satisfy this condition. If you have low angular distance, you want to have similar sparsity patterns. If you have high angular distance, you want to have conflict sparsity patterns. Okay. So let's look at the overall approach. So first of all, the first step is you need to partition the unit sphere using some points, which they call tessellated points. So let's say you have a bunch of points on the unit sphere, and then you partition the unit sphere into many regions like this. So imagine after this step you will get a picture like this. You partition the unit sphere into many regions like this. Okay. So after the step 1, we go to step 2. We associate each region on the unit sphere with a permutation of p-dimensional vector. So first we partition the unit sphere, and then we associate each region with a permutation of p-dimensional vector. So totally you have p factorial permutation, right? So meaning that you can associate each region here with one permutation. Okay. So now we go. So when the next step is you have a dense vector, you have a dense factor. You try to locate the region where that factor belongs to, right? So let's say you have a user vector or item vector here. You will need to locate which region that user vector and item vector belong to, right? And then you just add more zeros coordinates toward the end of the dense vector like this. So this one you get k-dimensional vector, and by adding more zeros value you get p-dimensional vector. Okay, and now you get this new sparse vector, right? You apply the permutation associated with particular region to get the dense, the new sparse vector. So you have the dense factor, right? Dense vector. You add more zero value to the end, and then you apply the permutation to get the sparse vectors. Okay. So now after this you will go from dense vector to sparse vector. Okay, from k-dimensional to p-dimensional. Okay. Yeah, but we have problem. In order to locate which region one particular vector belong to, you need to compute the inner product between that vector to all the point, all the tessellating points, right? Meaning that you need to check whether this one belongs to this area, this area or not. And it is also an expensive task because you need to compute with all the tessellating points on the sphere. And the second computational expensive task is you need to store all the permutation in the storage, which also take a lot of space in the memory. Okay, so we have solution. They propose a deterministic schema. So the deterministic schema will do something like they base on a base set like this, and then they construct the tessellating set through this procedure. So you have 3 elements in the base set, and then you construct all the k-dimensional combination from the base set to get a set of vectors which has k-dimensional, which are k-dimensional vectors, and then you normalize them. So now all the points are now on the sphere. So after this one, you can get a partition of the unit sphere like this, right? So for example, if in the case k equal to 2, right, you have set A, which is like this one, and you don't use concatenation which on the element are 0. Okay, so just minus 1, minus 1, minus 1, 0. So, and then you normalize all these vectors to get the set of decelerating vectors. And then based on this one, you start partition the unit sphere. Sorry? Then you just add 2 more value to this. So instead of having 5, you have now 4 to k, 4 to the power k minus 1. So it is proof in the paper that if you use this kind of schema, you can have a very efficient computational decelerating step, in which the complexity only depends on the dimension of the data points. It doesn't depend on the number of points. It doesn't depend on the number of decelerating vectors. So meaning that the only thing that is matter is the dimension of the original data point. Okay. So we can consider this as efficient schema. So with that, basically we can solve the first problem. Right. The first problem is it is very expensive to locate the position of one dense factor on the unit sphere. Now it can be solved effectively. The second problem, which we need to store all the permutation mapping for all the region on the unit sphere. So now instead of doing that, they construct a deterministic mapping function in which the input is associated with a particular region A and dense factor Z. So with that, you don't need to store all the permutation for all the regions on the unit sphere anymore. You just need to apply this deterministic function for each region. So with that, basically we solve the second problem. Okay. I know that it's difficult to understand, but I hope that people get some points from the whole procedure, the whole framework. So now we move on to the experiments. Could we reserve the question for the question answering session? We still have time for questions, so don't worry. The baselines mentioned in this paper are locality sensitive hashing, cheese indexing, commitment rank order. All of them are data structure which can be used to speed up the retrieval process for any recommender system. The data set, they have 2 data sets. The first one is synthetic data set, in which they simulate the user vector and item vectors from a normal Gaussian distribution. And then they construct the rating matrix using the linear product between the 2 matrices. So in the synthetic data, they have a complete rating matrix. And the second data set is mobilized data set. You have nearly 1,000 users, 1,700 movies, and 1,100 ratings. But it is not complete ratings matrix. And the 2 metrics they consider in this paper, the first one is recovery accuracy, which is a proportion of relevant items recovered. So after this, the framework, the model will discuss some irrelevant items, right? And then they do exact computation over the remaining items. So here is to measure the proportion of relevant items, which is kept in the remaining items. And the second metric is the percentage of discarded items, because the purpose is we try to remove as many items as possible. So usually which one can discuss more items usually is better. But we also need to consider the trade-off between the discarded items and the recovery accuracy. Because if we discarded all the items, then we can get zero accuracy, right? So the synthetic data. So the way they display the result is using histogram, because the percentage of discarded items varies from user to user. It's not similar, so they use a histogram to display the result. So as you can see that with synthetic data, the average value is around 80%, which are better than all other methods. If you compute the average value for all the methods, then right now the proposed model in this paper is better. And they do this combined comparisons. So as you can see that the black histogram here is of this model, and it is better than other methods. In terms of accuracy, recovery accuracy, it is also shown that the proposed model is better than all other methods. And similarly, we have, not similarly, in this case, then the percentage of discarded items over user are pretty much the same between this proposed model and the two AISTATS models. However, with the same percentage of discarded items, they have a better accuracy. So overall, we see that it is the model outperforms on the baselines. So moves to the discussion. So this paper addressed a problem in recommender system, which is recommendation retrieval. So I just want to highlight that having a fast recommendation retrieval system is important practical problem. And currently, as far I know, we have two different approaches. The first approach is post-processing approach, in which you can apply the post-processing step to any metric factorization models. And the second approach is you try to build an MF model in which the output is natively indexable. So you can use any kind of data structure like locality sensitive hashing or inverted index directly to the output of the MF models. So a couple of things in this paper which is I found it unreasonable. The first one is the order of items with respect to angular distance are not equivalent to the order that is with respect to the inner product. So if you compute the inner product between user vector to all the items, the order is not the same as the order you get if you use the angular distance, because the two metrics are not equivalent. That's the first problem. The second one is more about comment, which is presented in the paper, that you can have bigger set base. Instead of 3 elements, you can have D elements. So you can have a better partition of the unit sphere. And the true discussion question, which is the rating scale may affect the performance, because right now I think they assume that the rating scale are positive because the inner product can be smaller than 0. In this case, they assume that the smallest value for inner product is 0, which influenced by this rating scale. And the density of data points on the unit sphere also affect the performance, because if all the points are concentrated around the one point, then it is not reasonable to partition the sphere uniformly, right? Because you cannot discuss or you cannot remove all the points. And one open question is we can have theoretical analysis of the framework proposed in this paper, because it is not yet proof theoretically that it's going to guarantee the performance of all the data set. Okay, so with that I would like to end the presentation here. Thank you. So it's time for question.